work, but why it's not superconducting? Well, this is oversimplifying it a little bit, but in the spirit of the meeting and also of Thomas's talk, I will of course also talk about a little bit what has been done over the years, because I think this is like a much more general topic. And so I have to do it by hand. I think I can be very quick on this slide. We know the typical structure for high TC. We know the very rich generic phase diagram. And then the question is, of course, how can we model that? A complete description is completely unfeasible and probably would be uninformative, because for that we have the experiment that is already the complete description. So the model, in some sense, should capture the essential concepts in the mechanism, or as Einstein once said, a theory should be as simple as possible, but not simpler. So, I mean, what has been done over the years is basically that it has been simplified to the 3-band model, and then from the 3-band model, we can go to the single-band model. This is, of course, one question that also comes up. Is the single-band model perhaps too simple? But let's start to be as simple as possible. So we would end up with a single-band Hubbard model on a square lattice, hole doping, just nearest neighbor hopping and on-site repulsion. That's as simple as it gets. And the question is that enough? So we know it has antiferromagnetism. We've heard a lot about pseudo-gap behavior in the previous talks, and also about the role of T prime there. We have heard about finite temperature. So in this talk, it will be at 0 temperature. It will be about the presence of stripes, the presence of power law, E-wave superconducting correlations, which then coupling in 3D with long-range order. And then sort of like I will do this in a series of steps, if time allows, of complexifications of the Hubbard model. So I will start with T prime equals 0, no next nearest neighbor hopping, and then move to T prime non-zero. From a condensed matter physicist point of view, this may all be a bit weird, because well, in the electronic structure calculations show us that there is a T prime that is non-zero, and the question is just whether we get away with not using it. But if you take the point of view of all these ultra-cold atom experiment guys, there this question is absolutely essential, because at least at the moment they are absolutely clueless how to do a T prime that is not equal to 0. What are you saying? Let's keep it. We can keep that for discussion. Okay, so the temperature is heating up. That's good. So so that no one is jet lagged and is falling asleep. So I think we can agree on this naive picture. We have the antiferromagnetic order. We dope a hole. When the hole starts hopping to lower kinetic energy, this of course creates frustration of the antiferromagnetic order. So that's not so nice. So what can we do against that? And there's of course two ideas which go back to the very early days of ITC 88, 89. Well, you have a correlated pair hopping, and then these pairs ultimately will form the superconductor. On the other hand, you could form a stripe with a high hole density and a low magnetic moment, where they can basically do whatever they want. We have heard that in many talks. The question which of course you could ask at this point is, are they in cooperation or are they in competition? I will get back to that point as well. Now, there has been an enormous amount of work on that, and so I cannot really discuss that. Here, this will take a few evenings and nights probably. So, and also all this is in small print, so you have no time to find whether your paper is on it or not, and then you have to hate me for it or not. So let me just say, extremely good people have used extremely powerful methods, and there was no real agreement. And so what I want to show as the first kind of sort of like detailed work where I was not involved myself, but which basically reflects, in my view, the spirit we should take in the field in the future, is this one of the papers of the Simons collaboration of the many electron problem. This idea that we should not just kind of take this method and that method, but we should basically try that these various methods which we have should mutually support each other. We should not only acknowledge the strengths of our own methods, but also their weaknesses. I think this point is very important. And these people got together and did that for the kind of simple Hubbard model. We call it in a later paper the pure Hubbard model, which is of course unrelated to the doping, just that there's no T prime. For U equals 8T and 1,8 hole doping, bringing together these four methods, EMET, DMRG, IPEPS, and auxiliary field QMC. And what I just want to point out, without going into full detail, is that you can, of course, qualify all these methods by their various excuse me, properties. The point I want to make is I want to go right away to where they have a problem with an error. And in the AFQMC, for example, is they have to implement a constraint, which they do not control well. UNet has a problem with cluster size. DMRG has a problem with the cylinders it can treat. I will get back to that in more detail. IPEPS has perhaps also a problem with cluster size. Philippe just told me that he thinks the main problem is not the size of the clusters, but the bond dimension. But this is exactly the spirit. We should be critical of what we are doing ourselves. So just to cut a long story on a long paper short, is what these guys showed, that they have very good agreement about the ground state energy also at doping, not just at the easier case of bar filling. And sort of like what is perhaps more important than energy is that they also were able to agree very well on what they see in this particular model as the ground state. Namely, what they see a stripe phase. And this is taken from that paper. And as you can see, it's a period 8, lambda equals 8 stripe, which they see. This is where these methods agree more or less on having the lowest energy. I say more or less because there's a very interesting aspect that mainly stripes of period 5 to 8, thanks a lot, have more or less the same energy. So they're very close to each other in energy. And this is, of course, at variance with these many experimental results going back to 95, that what you really find is a half-filled stripe of period 4. What is also quite clear in these simulations is to see that's what where the lambda 4 sits. So this is definitely higher than these energies. The pure D wave would be sitting, I think, around here, if I remember the numbers correctly. So this is definitely, there is definitely stripes as the ground state. So moving on from that study, and this is basically where I want to talk a little bit more about, because it's what I was involved in, is that we take the same point in the phase diagram, the U equals 8T, doping 1A, and we move on to ask questions about the pairing order, the superconducting correlations. There, of course, also have been lots of papers, again in small print, so that you cannot really check whether we are on there or not. Here it says many more. And then, of course, the question of stripes and superconductivity. Here, this was in a more restricted set of methods, namely AFQMC, done by these gentlemen here, meeting DMRG, done by these people here, including myself, and this was on the archive recently and is currently with the referees. Before I go into the results, let's stay in the spirit of kind of acknowledging the strengths and the particular weaknesses of the methods. I will be relatively brief on DMRG and MPS, because I think there I can answer all additional questions if necessary without slides. And I think most of you have been exposed to these typical MPS talks about one-dimensional variational ansatz of matrices being multiplied to each other. So we'll focus right away of what you have to do to go to 2 dimensions. So what you do, going back to Steve many decades ago now, is you map the 2D lattice to a one-dimensional, say, snake, which then has, of course, effectively long-range interactions. And what the ansatz has to model is the entanglement that is present in the state. And so now I can cut the system into 2 along this line. And there, this is good. We expect that the entanglement grows linearly, area law. And here we have a linearly growing number of matrices being multiplied to each other across these bonds to capture this entanglement. Fine. If we want to introduce periodic boundary conditions, we get an additional cut down here. So we need some more ansatz parameters to capture that as well. This is extra cost, which is why DMRG people don't like periodic boundary conditions, but if you press them, they can do this. The problem is, of course, that if we cut along here, this one single bond has to capture all the entanglement which is happening across this blue line. And we know from DMRG theory or MPS theory that essentially that means that the bond dimension or the size of these matrices has to grow exponentially with the width of the system. So effectively, this means we can make long stripy-like systems, and in order to minimize open boundary effects along the short distance, we make it periodic, which means what we are looking at is ultimately cylinders. And these cylinders are small. With 4 cylinders for the Hubbard model are kind of comparatively easily doable. I mean, they're not trivial either. And width 6 is extremely hard, and width 8 is currently impossible. Yeah, so this is sort of like where we stand there. Let's now move to AFQMC, where I'm not an expert, so this is kind of a layman's view on it. So basically what you do is you look at the ground state by an imaginary time evolution of trial state. You do that in the simplest version using Slater determinants. If you want to evolve them and stay within the realm of Slater determinants, you need a quadratic Hamiltonian. Well, what do you do with the interaction? You do a Hubbard-Slatonovich, which introduces auxiliary fields. This is the decoupling. These X's are the auxiliary fields, and that, of course, you can now sample stochastically. This is where quantum Monte Carlo comes in. And then you evaluate, say, your ground state. Well, look at this picture here, which is from Shive. This is where the energy, well, you look at 4 times 4, 1, 8 doping, U equals 8, and then the energy doesn't look good at all. Well, this is the famous sign problem. So the question is, what do these guys, the AFQMC people in particular, do about it? Well, so they do something which is called the constraint path, AFQMC, where basically the idea is that if your trial wave function evolves in imaginary time and it hits at some point a line, an imaginary line, where it has 0 overlap with the exact ground state wave function, it will stay 0. Just insert an e to the minus beta h in here. This will stay 0. And this is no problem because analytically it's no problem if you do your auxiliary fields in some way exactly. What this just means, there will be paths with these plus and minus fields that will cancel each other exactly. The sign problem now comes from the fact that in the sampling, they will, of course, no longer cancel each other exactly. That's the problem you have to solve. So what these guys do is they say, I keep only paths that stay on the one side. You can show that this is in principle sufficient. This is basically this constraint path idea. The problem is, of course, they don't know where this line lies in space. So they have to basically approximate this nodal structure by a trial wave function. But this can work extremely well. So this is sort of like this kind of ugly curve which we had before, and now they introduce their constraint in a smart way, and now the energy curve looks very nice. But this is, of course, the kind of the weakness of this method, whether they do this properly. And these are the 2 methods we are now applying. And for this paper, we used several improvements of the method, which are quite technical, so I will only briefly mention them here. If someone is interested, I'll discuss that in more detail. My group is mainly using something called the single side EMRG, where you do not sweep 2 sides, as you have probably seen it in many talks, but only a single side. This is roughly 4 times more efficient, which is important here. But there are issues of the convergence to the true state. We had an idea to improve that convergence dramatically a couple of years ago. There's also an issue of error monitoring in this single side EMRG, which is why people didn't really like it. But we have overcome that in our work 2 years ago. So now I think it's a really kind of fully fledged method one can use for Shive-Sang's and for workers' work. A big step forward was to switch from these later determinants to BCS-like trial wave functions, and ultimately to be able to calculate the pairing order parameter, the two-wave pairing operator from total energy calculations. And energy is, of course, the quantity that they get more precisely, most precisely. Now, our strategy in this work was, in the spirit of this collaboration, that we use quasi-exact EMRG results on the smaller cylinders, which we can rely on, up to width 6, to check AFQMC, whether their strategy for the constraint path is a good one or not, because this is where they are weak. And then they do what we cannot do. They go to the thermodynamic limit, which I put in quote unquote. Of course, this is not infinite size, it's just much larger clusters than what we could possibly do in DMRG. So which quantities do we measure? So we apply, there's three different things which we are doing. First is we apply a global pairing field and observe the pairing response. And then, of course, we take the bulk pairing field to 0 and do the proper extrapolations. The second approach is to apply a pairing field just at the edge of the system and see how the pairing decays into the bulk. And the third thing, which of course gives the weakest signal numerically, is to, and therefore it's only in DMRG because the statistics is not good enough for I think, is to look at the decay of the pair-pair correlations. Okay, so what do we get? Out of the many curves, I will only show a few and then one example how we gauge each other. So if you look at this edge pairing field, so one example, for example, from a 48x4 cluster was sort of like this decay, where sort of like with increasing bond dimensions, we could see that it converges, and then it definitely to us looks exponential. Here in this inset up here, you see that up to a sign, which we of course introduced, you also have the typical plus minus structure of the D-wave correlations. On 48x6, we essentially get the same results for a pair-pair correlation. Sort of like this is sort of like what you can do with DMRG. Actually, these 22,000 states are SU2 states compared to the usual counting of DMRG states. That's about 70,000 states. In the meantime, we have gone up to 100,000 or something like this. But you see, even then, this still has to be extrapolated quite a lot to get these curves. So these bond dimensions really matter to be able to go up to these kind of simply crazy numbers. So that all would suggest no D wave. So now let's look at what happens if we take this to larger systems. So first of all, I want to show briefly how we gauge each other. As I said, the HPMC people now do the order parameter by looking at a derivative of the energy, like via the Hellman-Feynman theorem. So first of all, we have to get the energies properly, and then of course the derivative. And this is on relatively small systems, but these were the figures I could most easily pull up for this talk. And the agreement between the energies is extremely good. Also, the derivative between, of course, the numerically shakier quantity is also very good between the two methods. And incidentally, we see that the strongest response to the pairing field was around doping 1/8, which is why we are actually also focusing on that region. Now, what, of course, the AFQMC people, once they have left us DMRG people behind, what they have to do is they look at all sorts of finite sizes up to 16 times 12 and 32 times 8. There's various aspect ratios in here for various pairing fields. And then, of course, you have to extrapolate that. And as you all know, the order of extrapolation matters in order parameters. So first of all, for each pairing field, you have to take the thermodynamic limit and then take finally the field to 0 in these results. And what they find is that consistent with what we got in the DMRG results for this bulk pairing and response and pairing correlations, there is no pairing order that survives in the thermodynamic 0 field limit. Okay, that's basically what we would say about this. Let me briefly mention that by playing around with this pairing field, which of course tries to enhance the superconducting order, you also get some idea of what swipes and superconductivity do to each other. And what we find is the stronger we make the pairing and enforce superconducting correlations, the weaker the swipe amplitude gets. So we would effectively from this data conclude that they are in competition. How much more time do I have? 5 minutes. Okay, so I will. 5 minutes, 45 seconds. Okay, so I will jump what we found at U equals 4 doping 1/6. This is actually a typo. Sorry about that. There we found that there is maybe, there's no stripes, but there is possibly very weak superconductivity, but we really focused on these values of U that and even higher values that we I think are most relevant to the Cook rates. But this kind of would be a further discussion, but the numerics was very unclear there. These are no cheap calculations, so we had not much time to go through the full set of possible parameters. Okay, let me then briefly switch on T prime. Okay, this is again probably round one with contradict, but no, there you don't. So it was something else that you didn't like. We will get to that in the discussion. But anyways, it's the same gang again. This is work in progress. As you will see, at the moment we are a bit unconclusive. But so as I also promised to show other people's work, I will concentrate on two papers. The one is wonderful work by Philip, who is in the audience and can comment afterwards, as I have only 4 minutes left. Please do it after. He looked at various supercells of IPEPs which stabilize different stripe structures, comparing their energies. He finds that in a wide range of T prime, he gets the lambda equals 4 stripes, and actually with quite a distance in energy. And if he then goes into this width 4 stripe, he can stabilize D-wave pairing at a doping which is a bit above, say, 0.14 or something like this, with the strongest signal, say, 0.2 to 0.2. So this is the one work I wanted to mention. The other one is the work by Hongcheng Zhang, and I think you from Iran. Yeah, exactly. And this is sort of like DMRG on width 4 cylinders with a T prime of minus 0.25. And what you can see here is, for different views, is first of all, they have period 4 stripes as you want them. You see here, this is basically pair correlations, where on a cylinder, the bonds sit like that correlate with each other. We have to get back to that in a second. And they see very clear and beautiful power law decay of the pair correlations. And this is at this point, however, I think we have to look a bit again at the special topology of with 4 cylinders, which actually Steve tells me he already had this in work with Steve in the late, with Doug Scalapino in the late 90s. So we all know that in this TV studies, it's like an Orwell's Animal Farm: 4 legs good, 2 legs bad. 2 legs is certainly not enough. The question is really 4 legs good enough? Because what you can do is you can think about 2 types of E-wave only on a width 4 cylinder. This is very specific to a width 4 cylinder. You have either sort of like here, this would be plus and minus pairing correlations. This would be a D-wave which sits on the surface of the cylinder, which is one which you can extrapolate to 2 dimensions. And on the other hand, in the width 4 cylinder, you can of course also put D-wave on these plaquettes here. This is of course essentially a one-dimensional feature, and somehow they will of course compete with each other and interfere. And for the thermodynamic limit in 2D, we are of course interested in that one. So if we now sort of like look at these pairing correlations, what we find is, if you look at the sort of like the blue and the red curves are plus and minus of the correlations which you get this one with this one, this one, or that one with that one, or that with that one, that one, that one, and they are exactly identical up to the sign, which to us suggests that this superconducting correlation with the power law is actually the one which comes from these plaquettes. And this one here, the orange and the green curve, that correlate basically what you would expect from the D-wave, which has this structure here. And there we find an exponential decay. So my suspicion at the moment is that the width 4 cylinder power law decay is probably rather a one-dimensional effect. So this is so will certainly lead to debate, but that's what I expect. So, but in any ways, to be sure about it, we should probably, and actually, sorry, I probably have to jump that slide. I could enforce that statement by playing around with T primes in various weird locations where you can enhance and suppress superconductivity of these various sorts as you wish. In some sense, this has already been seen in the TJ model a long time ago by Steve, but I jumped that. So Then I adopt sort of like saying, well, Orwell's Animal Farm saying 6 legs good, 4 legs bad. Maybe this is all wrong, but now this result I don't like either. So here, this is what DMRG currently tells us on the width 6 cylinders, where the decay of the pair-pair correlations looks exponential. Okay. So I could say, well, this is what my method shows, and therefore it must be like this. But well, as we have seen, the decisive point is that we try to get these various methods to agree with each other. So again, we try to build the DMRG and AFQMC connection, and this is currently very challenging. For 4 legs, the agreement between the 2 methods is actually excellent. Just one picture here is the response of the pairing to a pairing field. The one line is DMRG and the other one is QMC. So this looks very nice. And on 6 legs, to be very honest, we simply have disagreement. And we are currently exploring why. This is in the early stages. I'm very willing to admit that I personally have doubts about the DMRG results, but we have to see that. AFQMC, it seems, has a tendency to show the power law decay, and D-wave subconductivity and DMRG, as you have just seen, does not. But it might simply be that DMRG is not yet properly converged. And by that, I do not mean in the bond dimension. But what many people forget is that you start from some state and then you do this DMRG sweeping. And whether you are actually in the true ground state or not, this is a different story. You need to then increase the bond dimension to say 1 billion. This will not make any difference anymore. So this is really the point we have to attack. On width 4, it's relatively simple to get into the right states. On width 6, I've seen quite a lot of wrong results in the past. So there we have to be very careful. So the message here is to be continued. So the conclusions, and then I'm done, and I'm probably 1 minute over or so, is our claim is that this pure meaning time equals 0. Our model does not show D-wave superconductivity. For the relevant parameters, it's different in the small u regime. So that it seems the cold atom people who read the paper don't like it, because it would mean that their experiments are probably in trouble if they claim they do IPC. I would have said they have a temperature issue anyways there. So in this, if you switch on the T prime less than 0, IPEPS finds period 4 stripes pairing order. The DMRG results for width 4, I think they are all correct, which we have, but my fear is that they might be irrelevant. But width 6, which would be the natural answer to that, I have to say we are not consistent at the moment, and this is of course where it gets exciting to continue that. Thank you very much.
I just wanted to add a comment. When we look at the same thing that you already mentioned, we do still see power law at least for memory behavior, but the correlations are weaker. So there are strong.
Yeah, but I mean, I think this definitely we have to see that we get. I mean, we would have to look at the data, but I definitely think the message is really we have to look at these wider cylinders and try to get it into agreement with, say, AFQMC or one of the other methods. Because I think for the width 4, we have this, as there also was mentioned in many papers, is of course this weird interplay between these various D-wave orders. So these results sort of like they have something to say, but sort of like you can really suppress this plaquette problem only on width 6 onwards. Yeah. Thanks.
Is there any hope of going to slightly different or somewhere where you can actually find some conductivity and then gradually two parameters?
Yeah, I mean, this is basically where sort of like I set up that I said U equals 4 and the doping 1/6, where it seems that there is a very weak superconducting order. So you wonder if you go a little bit lower, might be stronger, and then you do exactly what you say. That would, of course, be an extremely interesting avenue to pursue. But I mean, these calculations, as you've seen, I mean, these enormous bond dimensions, we really have to basically take our time to do that.
Yeah. So actually, how do you know that you're not? How do you detect that you're stuck in the local minimum?
Well, I mean, sort of like there are many relatively simple checks which you can use for the states that you could use, because many of them I've seen were simply wrong on a very obvious level. Like, say you know that you expect a certain symmetry or anti-symmetry in certain physical quantities because you have left-right parity, and these states will simply start violating that. I mean, it starts at simple tests like that, and then you can, of course, try to mirror the wave function and see, because I mean, this is, of course, possible, what the observables look like. And there's many things you can test at this simple level, of course, but ultimately, of course, we never know except for the comparison with other methods.
Do you do activity field, or do you try to get the
Actually, a long time ago, I was quite ambitious to try it without pinning fields, because I sort of like didn't really like the idea of the pinning fields. I've seen sort of like stripes forming of various lambdas. At that time, I thought it's just that the method was bad. Maybe it was even correct now that we know that these energies are almost degenerate, so maybe it was even not wrong as a result. But I have been converted to the pinning field by this one paper where Ehlers, Noack, and White showed that you may have the problem that sort of like states, while you increase the bond dimension, they may actually cross in energy. So you may start out in the correct state at low bond dimensions, but then it becomes the incorrect state. You will not be able to basically to switch into that downturn. And this is something which, of course, you avoid by the use of pinning fields. That you say, okay, of course, I've biased the system, but I turn that into a strategy. So basically, really to explore many different states.
Thomas? Quick question. The AFQNC for the grid state system, you said that was power law correlations. Is this in the presence of atoms, right?
That honestly, I have not yet. So what they do is what they see. Okay, they do not look at the pair correlations, but at the response to this to the bulk field, and there it would look like they see the wave. And the other question is sort of like the lambda equals 4. I have to check, because this is really ongoing work at the very moment. What they have there, because we are worried that I think that to get the DMRG results consistent.
I think this is a simple question. So is that no superconducting statement in the pure quantum model inconsistent with the quantum cluster theory or quantum calculation? Or they actually agree, maybe because of the different periodic conflict, the periodic conflict is more open conflict, or by the stripe, the suppression by the stripe monsters?
Well, I mean, we had this discussion a couple of weeks ago at another meeting, in some sense, about what, for example, DMAT and these theories say that there was a certain suspicion that sort of like embedding the self-consistent embedding methods might have a tendency to emphasize order. But ultimately, the conclusion was that, for example, Garnet, John wanted to go back and run more simulations to be able to make these comparisons more consistently, because it would again be nice to have an agreement between all the methods, like in this 2017 paper. Well, not all the methods, there are many more, but a substantial number. So there is this.
Can you repeat louder the question?
I understand these are zero contributor calculations, but should you say anything about the string the energy scale for the
No, not really at the moment.
So I suggest we thank the speaker for his talk.